The year is 2025, and while you're watching this video, the fastest human-made object in history is hurtling through space at over 430,000 miles per hour. Yet even at that incredible speed, it would still take this spacecraft over 6,000 years just to reach our nearest stellar neighbor. This isn't science fiction anymore. This is the reality of interstellar travel. And the question isn't if we'll reach another star, but when and how we'll overcome the most challenging journey humanity has ever attempted. Right now, as you sit there, Proxima Centauri, our closest star beyond the Sun, is sitting 4.24 light-years away. That might not sound like much, but let me put this into perspective that'll blow your mind. If you could drive a car to Proxima Centauri at highway speeds without stopping, it would take you 50 million years. If you traveled on the fastest commercial airliner, you'd still need 5 million years. Even our most advanced rockets today would require tens of thousands of years for a one-way trip. But here's where it gets fascinating. Scientists and engineers around the world aren't just dreaming about interstellar travel anymore. They're actively working on technologies that could make it happen within this century. And some of these concepts are so revolutionary, they're rewriting what we thought was possible. The challenge of interstellar travel begins with understanding just how empty and vast space really is. When we look up at the night sky, stars seem relatively close together, but that's a cosmic illusion. The space between stars is so enormous that it defies human comprehension. Our entire solar system, from the Sun to the edge of the Oort cloud, spans about 2 light-years. Yet the gap to our nearest neighbor is more than twice that distance. To make matters more challenging, space isn't actually empty. The interstellar medium contains dust particles, gas atoms, and cosmic radiation that would pose serious threats to any spacecraft traveling at the extreme speeds necessary for interstellar journeys. At just 1% the speed of light, a grain of dust would hit a spacecraft with the force of a hand grenade. Cosmic radiation would bombard any human passengers with lethal doses over the course of such a long journey. Yet despite these challenges, several groundbreaking projects are already underway. The breakthrough Starshot initiative, backed by Stephen Hawking before his passing and funded by billionaire Yuri Milner, represents one of the most promising near-term approaches to interstellar travel. Their concept involves using powerful lasers to accelerate tiny spacecraft called light sails to about 20% the speed of light. These aren't spacecraft in the traditional sense. Each probe would be about the size of a computer chip, weighing just grams with an ultra-thin reflective sail. Arrays of powerful lasers on Earth would focus their beams on these sails, pushing them to speeds of 134 million miles per hour. At such velocities, these miniature explorers could reach Proxima Centauri in just 20 years. The technology required for breakthrough Starshot pushes the boundaries of current engineering. The laser array would need to generate about 100 gigawatts of power, equivalent to the output of a large nuclear power plant, all focused into incredibly precise beams. The light sails would need to be manufactured from materials that can withstand enormous accelerations and the harsh environment of interstellar space while remaining impossibly thin and light. But even if breakthrough Starshot succeeds, these tiny probes could only send back data, not humans. For human interstellar travel, we need to think much bigger and more ambitiously. This is where concepts that sound like pure science fiction enter the realm of serious scientific consideration. Fusion rockets represent one of the most promising technologies for human interstellar travel. Unlike chemical rockets that burn fuel and oxidizer, fusion rockets would harness the same nuclear process that powers the sun. Hydrogen atoms would be fused together, releasing enormous amounts of energy and allowing spacecraft to achieve speeds of up to 10 to 15% the speed of light. The physics of fusion propulsion are well understood, but the engineering challenges remain formidable. We're still working to achieve controlled fusion reactions on Earth for power generation, let alone for spacecraft propulsion. However, recent breakthroughs in fusion research, including the achievement of net energy gain at the National Ignition Facility, suggest that fusion-powered spacecraft might become reality within the next 50 to 100 years. With fusion propulsion, a journey to Proxima Centauri could take between 30 to 50 years instead of thousands. This opens up the possibility of generation ships, massive vessels carrying thousands of people on interstellar journeys. The passengers who begin such a voyage might not live to see their destination, but their children or grandchildren would. Generation ships present their own unique challenges beyond propulsion. These vessels would need to be entirely self-sufficient, recycling air, water, and waste while producing food for decades or centuries. They would require robust artificial ecosystems, advanced manufacturing capabilities, and social systems capable of maintaining stability across multiple generations in the confines of a spacecraft. The psychological and social challenges of generation ships might prove even more difficult than the technological ones. How do you maintain motivation and purpose across generations of people born in space? How do you prevent social breakdown or technological failure during journeys spanning human lifetimes? These questions require careful consideration from sociologists, psychologists, and ethicists, not just engineers. Another revolutionary concept gaining serious scientific attention is the antimatter rocket. Antimatter represents the most energy-dense fuel theoretically possible. When matter and antimatter collide, they annihilate each other, converting their entire mass into pure energy, according to Einstein's famous equation, E equals mc squared. This process is millions of times more efficient than chemical reactions and thousands of times more efficient than nuclear fusion. An antimatter rocket could theoretically achieve speeds of 50 to 70% the speed of light, reducing travel time to Proxima Centauri to just 6 to 8 years. However, antimatter propulsion faces enormous practical challenges. Currently, we can only produce tiny amounts of antimatter at facilities like CERN, and the cost is astronomical, literally trillions of dollars per gram. Additionally, storing antimatter safely presents unprecedented engineering challenges, as it must be kept from touching any normal matter or it will immediately annihilate. While we work on these advanced propulsion systems, some scientists are exploring even more exotic possibilities. Solar sails and magnetic sails could harness the radiation pressure from stars or magnetic fields in space to provide continuous, though gentle, acceleration. Bussard ramjets would scoop up hydrogen from the interstellar medium to fuel fusion reactions, essentially refueling during flight. The most speculative concepts venture into theoretical physics that pushes the boundaries of our current understanding. Alcubierre drives would manipulate space-time itself, contracting space in front of a spacecraft and expanding it behind, allowing faster-than-light travel without violating relativity. Wormholes, if they exist and could be artificially created or stabilized, might provide shortcuts through space and time. These exotic propulsion concepts remain firmly in the realm of theoretical physics for now, requiring exotic matter with negative energy density that may not exist in nature. However, they represent the kind of revolutionary thinking that might eventually make interstellar travel as routine as air travel is today. Beyond propulsion, interstellar missions face numerous other challenges. Communication with Earth would involve delays measured in years. A message sent from Proxima Centauri would take over 4 years to reach Earth, making real-time mission control impossible. Spacecraft would need unprecedented autonomy and artificial intelligence to make critical decisions without human guidance. Navigation across interstellar distances requires precision beyond anything we've attempted. A navigation error of just 1 degree would miss the target star system by hundreds of billions of miles. Advanced sensors and course correction capabilities would be essential, and the spacecraft might need to adjust its trajectory multiple times during the journey based on increasingly accurate position measurements. The selection and design of target star systems adds another layer of complexity. Proxima Centauri, while closest, is a red dwarf star prone to violent flares that could sterilize any planets in its system. Other nearby stars like Alpha Centauri A and B, Barnard's star, or Wolf 359 might offer better prospects for finding habitable worlds, but they're located even further away. Recent discoveries of potentially habitable exoplanets have provided exciting targets for future interstellar missions. Proxima Centauri b, located in the habitable zone of our nearest stellar neighbor, represents the closest potentially Earth-like world we know of. TRAPPIST-1, located 39 light-years away, hosts 7 Earth-sized planets, several of which might have conditions suitable for life. Kepler 452b, sometimes called Earth's cousin, orbits a Sun-like star in the habitable zone, though it's over 1,400 light-years distant. The search for life in these distant worlds adds urgency and excitement to interstellar travel plans. If we discover evidence of life, or even civilizations, on nearby exoplanets, it would transform interstellar travel from scientific curiosity to one of humanity's highest priorities. Current and future telescopes, including the James Webb Space Telescope and planned ground-based, extremely large telescopes, will search for biosignatures in exoplanet atmospheres, potentially identifying the most promising targets for interstellar missions. Robotic Precursor missions will likely pave the way for eventual human interstellar travel. These automated scouts could survey star systems, identify potential hazards, and even begin preparing infrastructure for human arrival. They might deploy solar panels, establish communication networks, or even begin terraforming processes on suitable planets. The timeline for human interstellar travel depends heavily on technological breakthroughs and societal commitment. Conservative estimates suggest that fusion-powered generation ships might be possible by 2100 to 2150, assuming steady progress in fusion technology and materials science. More optimistic projections, banking on revolutionary breakthroughs in propulsion or exotic physics, suggest human interstellar missions could begin by 2075 to 2100. However, interstellar travel isn't just a technological challenge, it's also an economic and political one. The costs would be enormous, likely requiring international cooperation on a scale never before attempted. The resources needed for interstellar missions might rival the gross domestic product of entire nations. This level of investment would require long-term commitment, spanning multiple generations of political leadership. The benefits of interstellar travel extend far beyond scientific discovery. Establishing human colonies on other star systems would provide ultimate insurance against existential risks on Earth, from asteroid impacts to supervolcanic eruptions to human-caused catastrophes. Interstellar colonization would mark humanity's transition from a single-planet species to a true spacefaring civilization. The technologies developed for interstellar travel would revolutionize life on Earth as well. Advanced propulsion systems could make solar system travel routine and affordable. Life support systems designed for generation ships could improve sustainability on Earth. Autonomous systems and artificial intelligence required for interstellar missions would have countless terrestrial applications. As we stand at this crucial juncture in human history, interstellar travel represents both our greatest challenge and our most inspiring opportunity. The engineering problems are immense, the timescales are daunting, and the costs are staggering. Yet for the first time in human history, we can envision realistic pathways to the stars. The question isn't whether humans will eventually travel to other star systems, but when we'll develop the technology and muster the collective will to attempt such an extraordinary journey. Every breakthrough in fusion research, every advance in materials science, and every discovery of potentially habitable exoplanets brings us one step closer to becoming an interstellar species. Perhaps most remarkably, some of you watching this video might live to see the launch of humanity's first interstellar mission. The children and grandchildren of today's viewers might be among the first humans to set foot on a planet orbiting another star. We stand at the threshold of the greatest adventure in human history, and the countdown to our departure for the stars has already begun. The journey to reach another star will test every aspect of human ingenuity, determination, and cooperation. It will require us to overcome challenges that seem impossible today, just as powered flight seemed impossible 150 years ago. But if history has taught us anything, it's that human creativity and persistence can overcome even the most daunting obstacles. The stars are waiting, and humanity is preparing for the ultimate voyage.